I think the sixth session of Fiat radiation. Yeah, so as usual, it's just me and Kishore, and we'll start with Kishore presenting his. He'll talk about information causality, and I guess we can just go ahead and start. Kishore,
Yeah.
you're
Can you
on.
see the slides?
Okay, yeah, I can see the slides.
Okay. So we know that the quantum mechanics is not compatible with relativity. And about this thing, I had talked in one of the earlier handouts. What if it does? It leads to a paradox. And what is the paradox? So the set of measurable non-local operators that basically shrinks. But we in lab, we measure many non-local operators. And this is not just one problem with the compatibility of quantum mechanics and relativity. For example, there are problems like quantizing gravity, like general theory of relativity and quantum mechanics. They are not compatible. So it is sensible to take a step back and look at a special theory of relativity and quantum theory at its basic level. A special theory of relativity is based on two simple or say clear-cut principles, and those principles are that physics will be same in every frame of reference, and speed of light, no matter what is the speed of the light source, it will be c, which is basically 3 into 10 to the power 8 meter per second for every observer. Do we have any similar physical statement-based structure for quantum theory? Actually, we don't have. So unlike STR, quantum theory is rather a description of its formalism. So you have been given a formalism, and according to that formalism, you can calculate values, do the calculation, and you can match it with the experiment. For example, they say that the system will be represented by a state in the Hilbert space, evolution will be unitary, measurement will lead to collapse of the state to one of the eigenstate corresponding to the observable which you measured. So basically, it's just a description of the formalism. Efforts have been made in the past to understand quantum theory in a geometric manner. For example, this paper, non-locality as an axiom for quantum theory, was used by Popescu and Rollrich to derive quantum theory in a geometric manner. But till now, no one, including the authors of the paper which I'm going to discuss, has succeeded. So we all know that quantum theory has been used and misused due to its popular knowledge by bloggers and all, and
Kishore,
different.
Kishore.
Yeah.
Yeah, so I wanted to say something. You know that one of my, well, you won't know, obviously, one of my colleagues told me that it has been shown that you cannot derive the quantum correlations with a finite set of physical principles or something like that. Are you
Yeah,
aware of this result?
I'm not aware of this thing, but yeah, I was talking to Dagomir, the person who is taking me the course on quantum statistics and measurement, and this slide I basically prepare this slide to present to him tomorrow.
Yes.
So as it turns out, I asked him that is it possible to derive quantum theory from a few basic principles, and this paper was written by him in 2010. The quite famous paper at that time appeared in Nature also. But he says that according to him also, it's not possible to derive quantum theory from a few principles. It's just not possible. That's what he says. His answer was also negative.
Oh,
So, for
okay.
example, the principle that I'm going to present will somehow distinguish between what is physical and what is non-physical, but it will not help you derive Schrodinger equation or other things. Like, for example, we have two basic principles in the case of special theory of relativity. And like as you have seen the books of Landau and everywhere, that if you assume those two principles, you can derive Lorentz transformation and everything, and like
Right.
everything how that force transform dynamics, kinematics, everything just follows from two basic simple principles. But for yeah, quantum theory, as it turns out, it's still just a description of the formalism, and deriving it in an axiomatic manner is still not possible. Like this is the current situation.
Okay, thanks. Yeah,
Yeah.
okay.
But I talked to a few more people, including my guide and all, and they said that somehow we need to get out of the Hilbert state structure, and like maybe so
Yeah, we'll
people
see. Yeah,
like
okay.
diverse
Why don't you
opinions.
carry on with your slides and we'll probably discuss it a little more in the end.
Yeah, but actually, yeah, it's quite interesting, and maybe later we can discuss.
Yeah, yeah.
Okay.
Thanks.
So quantum theory has been used and misused due to its popular knowledge that we all know. Even people from non-physics background happen to have heard terms like entanglement and superposition, and they will talk blah and various things about this. And some of the are you saying something?
No.
Okay. So some of the features of quantum theory which people think as typically quantum are like intrinsic randomness. You can generate random numbers from quantum using quantum theory. There is no cloning principle. There is trade-off between information and disturbance. There is possibility of secure cryptography and all. And these are some of the features which common public think of as typically quantum. But the striking features of quantum mechanics have also the striking features of these striking features have provided hope to the scientists to come up with some physical principle based on the formalism. So can we use intrinsic randomness or say the no cloning theorem as a, the fundamental principle which can help us derive quantum theory? So people try to come up with such things. And Popescu and Rollrich ask, is quantum physics the most general theory that allows violation of Bell inequality while respecting the no signaling criteria? So they thought maybe the non-locality, that is a fundamental thing. Means they thought basically non-locality could be an axiom to a start for quantum mechanics. And actually the answer was found to be negative. There is a broad class of theory which mimics typical quantum features like intrinsic randomness, no cloning, secure cryptography, and blah, blah, like different stuffs. But so like these things are not specific to quantum theory. Like there are other theories which people may think as super quantum or something. They also mimic those properties which are mimicked by quantum, which are shown by quantum theory. So what is the specificity of quantum theory? And the authors of this paper, they come up with an important principle called no signaling principle. And the beauty of this principle is that it generalizes no signaling principle. So we know that according to no signaling principle, if there are two parties who are space-like separated, then one's action can't affect another's action and so on. Like the events can't talk to one another. So, so the principle, the information causality principle generalizes the no signaling principle, and it is respected by both classical and quantum physics, but violated by more than quantum no signaling theory. So as you can see that it kind of gives you a plane, and the theories which are on one side of the plane are classical theory and quantum theory, and the theory which are on the another side of the plane are basically the theory which are non-physical. So it gives you kind of criteria to filter theory which are physical.
So can I make a small suggestion, please? Whenever you're talking to me like this, just turn on your camera instead of the presentation, because otherwise the screen looks very weird. A lot of me's are in the frame.
Yeah, but it's comfortable to me. Okay. Okay.
Okay. Yeah, just keep looking at the slide and talking. Then I mean, it doesn't help.
Then it's very stupid. Like, okay. Anyway.
Yeah.
So let's look at information causality. So it says that suppose Alice had some information and some subset of resources. Say Alice has some data set and sends part of the information to Bob. And what is the maximum data set that Bob can access? This is information causality about. So it says that information gain that Bob can reach about previously unknown to him data set of Alice by using all his local resources. Yeah, local resources. And M classical bits communicated by Alice is at most M bits. So it's very simple. It says that if Alice meets Bob,
show me the slide. I want to read that.
Oh, fine. So it says that it basically means that if Alice sends M bits to Bob, then Bob gets information of at max M bits. It seems very trivial, right? If I give you 1 bit, then you receive at max 1 bit. Nothing more, nothing less. No, you can receive less because of channel noise and all, but you can't receive more than 1 bit. So this is the principle of information causality. And you can say that for M equal to 0, it reduces to no signaling condition, which basically means that Alice has not communicated with Bob. So Bob will have no access to Alice data set. Right?
Yeah, information gain, but is it easy to define it for quantum? with, I don't know, entangled systems, this, that, things should get no trouble. Anyway, let's see. Okay, go on.
Yeah, so you can use like mutual information, and like there are things like in quantum theory you have von Neumann entropy, and all. Using that you can understand information and also. So like there is
Yeah, but those conditional entropies go negative and things, no? Something like that.
conditional entropy. Yeah, but as we can see in the we don't have to, at least in the calculations and all, doesn't seem. So I think you are talking about the paper by Winter where he had this stuff about conditional entropy getting negative, right?
Yeah, could be.
Yeah, so they had also some kind of physical interpretation that you gain the information even if I don't send you or something. But still, it does not matter to this paper. And as it turns out, the person who had written that paper about negative conditional entropy is one of the authors of this paper.
Okay.
And this paper was published later. Okay. So the bits communicated are classical, in this case, not quantum bits. So these things you have to keep in mind. So Alice and Bob, they talk through some M bit classical message, and Bob at max gets access to M classical bits. That's it. So to better understand information causality, let us look at a task. So Alice receives a string of n random and independent bits, represented through a vector A from which is A0 to n minus 1. And Bob receives a random value of B, say from 0 to n minus 1. And after this, Alice sends a classical M bit message to Bob. Bob is asked to give a value of the bth bit of Alice. So think of it this like, suppose there are 3 bits. Suppose the vector A consists of 3 bits, A0, A1, and A2. Then in that case, Bob will receive a random value ranging from 0 to 2, 0, 1, or 2. If Bob receives 1, then he will have to answer A1. He has to guess what is the value of A1. And Alice sends at max M bit message to Bob. Alice and Bob can share only no signaling resources. We will call these resources as no signaling boxes. So this is the situation here. So Alice receives this bit of number A0 to n minus 1. Bob receives any one of the value of B from 0 to n minus 1. And Alice sends M bit classical message to Bob. Alice and Bob share some no signaling boxes between them. And the task is supposed to be complete if Bob perfectly guesses the value of AB. So you understand the task?
So the bth bit, okay.
Yeah. So think it like if B equal to 3, then he will have to Bob will have to reveal A2.
No, so B is a number, or what is B? Is it like a set of numbers, or is it one number? Because it looks like a set of numbers.
Yeah. So Bob receives one of the numbers from this set of numbers.
You written B equal to something something, so I got confused.
Yeah. B belong. I haven't written. Actually, it's problem.
From the paper, but then it should not be wrong.
Yeah, it should not be. I think it's archived, but maybe some problem. Yeah. B is just one. B belongs to, actually in the description of the figure they have written B belongs to, but
so B belongs to one of these numbers, and he's supposed to get the bth A from Alice.
Yeah, exactly. So suppose A0 is 0, A1 is 0, and A2 is also 0.
All right, cool. So my question now is that so Alice can send some M classical bits, that I understand. What I don't understand is what do you mean by sharing non-local boxes? Sharing, so they're communicating, or I don't understand that.
So one of the things like sharing non-local boxes, you can think of it like they can share PR boxes or something, or say they can have entangled qubits with them. So
you're saying, okay. So basically, they can use quantum resources as well as classical resources, or anything with respects no signaling. Okay.
Yeah, but the only thing is that the resources should be no signaling resources.
Okay, got it.
Otherwise, that will lead to opening of other channels.
But so they can use PR boxes, right?
Yeah, they can use PR boxes because the PR boxes are a no signaling box.
Okay.
Yeah. So this is the thing, and so you can see here that there exists a protocol to solve the task, and we will see how it works. So Alice sends M bit message A equal to A0 to A minus 1 to Bob. Now you can see that Bob can guess AB perfectly whenever B belongs to 0 to M minus 1, right? Because Alice has sent the message.
What Bob can guess AB perfectly
whenever V belongs to this A0, because Alice sends an M bit message A0 to A minus 1 to Bob.
so A0 to A minus 1 is
So so you can see in this figure,
okay. Hold on. A is a vector. It's just so
the
A0
vector
to
it goes
A
from 0 to N minus 1.
so A0, the components of the vector, are they bits or is it a number?
So components of the vector, they are individual bits, and they can take value. A0 can take 0, 1, A1 can take 0, 1 or anything.
Okay, okay. So he's supposed
Yeah.
to get the first B bits,
Uh,
or
no,
is he supposed to get the Bth bit?
yeah, he's supposed to get the B8 bit. So think of it, suppose N equal to 10. Then in
I think
that case,
that can always happen, no? So if she is allowed to send M classical bits, she just needs to send one bit of what this B is. Oh, actually, she doesn't know what
doesn't
the
know
value of B is.
what particular value Bob has.
Yeah, okay, okay.
Yeah. So she sends the message, and then whenever B belongs to 0 to M minus 1, then in that case, Bob can perfectly guess because he has the information from the message which came from Alice.
Yeah, okay. Best case, yes.
Yeah. But for other values, he don't know. He doesn't know. So Bob can guess AB perfectly whenever B belongs to this thing, but he's bound to make a guess for B belonging to M to N minus 1, right?
But depends on the protocol, really. But okay.
Yeah, this is a protocol. So like C will send first M bits to Bob.
Ah, okay. So
And,
it's a protocol.
yeah.
Okay, okay, sure, sure. Then it's fine. So they're not
So,
using any no signaling or anything yet. Oh, for
uh,
the guessing, they will use it. Okay.
yeah. So since the no signaling boxes shared between Alice and Bob contain no information about A, there will be a trade-off between probability to guess different bits of A, right?
Okay. Yes.
Yeah. Suppose you write Bob's output by beta, then we can quantify the efficiency of Alice and Bob protocol through this number. So suppose Bob receives B equal to K, right?
Okay.
Then he will have to guess AK.
Yes.
Yeah. And Bob's output is beta.
Okay.
So the actual value of AK is AK, but Bob's output is beta.
Yes.
So how good the protocol is will be given by the mutual information between AK and beta, how much AK and beta overlap.
Yeah. Okay. Mutual information, I'm not so properly familiar with, but okay.
Yeah. So mutual information gives you the, so I should tell you some information calculus also. So normally, you know, this, we quantify information using entropy.
Yes.
And we suppose there is a random variable X, which takes different values with different probability P1 to Pn. We quantify how much information there is using this Shannon's entropy, summation over Pi log Pi with a negative sign.
Yes.
Then you define something called conditional entropy, conditional information, which basically says that given you know about a particular value of random variable, other random variable Y, how much information you gain when you know about X. So that is basically H of X given Y.
Okay. And what is the formula for it? You just put the same in the probabilities.
Yeah, so you put the same in the probabilities and you get there. And similarly, you find the same for the joint probability distribution where you have, and that you call it the joint, what you call it, joint entropy or something. And finally, we have this thing called mutual information, which is basically how much the information is common between one random variable and other random variable. So it's like the intersection of two different Venn diagrams. You can relate it to there.
Okay.
Yeah. So it basically says how much one random variable and other random variable are close with respect to information gain that I can have from them.
Okay.
Yeah. See. So this thing IAK beta. This thing is the standard mutual information between AK and beta. So how much AK and beta overlap? And we will say that the information causality seems to hold if this thing IAXB, where X is the message which Alice sent to Bob and B is Bob's resources, this thing is less than equal to M. So if the mutual information between Alice data set and everything that Bob has, which is basically the message from the Alice and the no signaling box which Bob has, is less than equal to M.
Okay.
Yeah. But this intuitive description is not theory independent. For example, you can see there is a B sitting here. So B will talk about a particular no signaling box and all, and we need to have some theory independent description.
Okay.
But as it turns out, it's very difficult to come up with a theory independent description. But if you follow a few, follow a few simple constraints, then it's possible to have a scenario where information causality will hold, and I can have an expression for the information causality.
Okay.
And these things you will have to like take on faith. I will I can derive them and all, but for that we will have to like talk it after hangout and all. Otherwise, the mathematics that will not let us complete the talk.
Yeah, we anyway just have 5 minutes. So
Yeah. Oh. Actually, there are a lot of things. Okay. So the first thing that, but it's intuitive. So it says that the first criteria is that the definition of mutual information that I have should be consistent with the classical case. So if Alice data set, if Alice part and Bob's part both are classical system, then in that case my mutual information formula should match with the Shannon's mutual information, right?
I was thinking about something else. I'm sorry.
Yeah.
Can you say it again?
So what I'm saying that suppose Alice system and Bob's system both are classical.
Okay.
Then the definition for the mutual information I will have should match with the Shannon's mutual information formula, because Shannon's mutual information formula is the formula for the classical.
You're trying to generalize something, so it should match with the already known special case. Yeah.
Yeah, classical case. Yeah. Right?
Yeah.
It's intuitive. Second thing is data processing inequality, which basically says that suppose there is some information in a system called B, and if I process the data, then as a result of processing, I will not increase the information content of the system. I will only lose information. So suppose you have a CD drive and you process it, you don't like, yeah. And the third thing is a chain rule which is about some information. And basically, if you follow these three different
chain rule, I'm sorry, I did not understand.
So the chain rule is about some.
Back to the slide. Thank you.
Yeah. So chain rule, I will have to write on and explain to you. Like you will have to.
Okay, we'll do it later. It's okay.
Yeah. So it's basically a relation between. Suppose you have three different systems: Alice, Bob, and Charlie, and then it's a relation between mutual information between Alice and Bob and Charlie. It's just a mathematical definition.
Okay. So
Yeah.
what are you?
So basically, you have to, it basically says that mutual information between Alice and Bob and Charlie taken together should be equal to mutual information between Alice and Charlie, and Alice and Bob, given that Bob knows about Charlie.
Okay. Some structure of that sort. Yeah. Okay. Makes some sense. Yeah. Okay.
Yeah. Even if you don't like think about it, like if you assume these three things and take it on faith that information causality holds, like there is mathematics to prove it. Like I can prove it.
Okay, that's nice.
So information causality holds, and this I is less than equal to M. So the I that I defined right here,
we can make it more theory,
which does not have any X or like anything theory dependent structure. This I, this I becomes less than equal to M.
Okay, awesome, brilliant.
Yeah. So I have a parameter which looks like which is what do you call that? So CSSH, like the CHSH has been put in operational terms. Like there is no theory dependent structure in CHSH inequality and all. So this is a similar kind of parameter based quantification. So it does not depend on the underlying theory, whether it's quantum theory, classical theory, or say super quantum theory.
Okay.
Yeah. So following these three criteria, information causality holds and I less than equal to A. And you can see that the the claim by the authors is that the information causality is respected by both classical and quantum physics and other no signaling theories. They violate information causality.
Okay.
And
Other meaning all others.
yeah, all others. So like anything which is more than quantum, that will violate the quantum information. That will violate the information causality.
Wow. So then don't we already have a principle from which we can we can't derive it. We can just verify it. Okay. Okay.
Yeah. So it gives you kind of, like that's why I say it gives you kind of wall. So on one side of the plane there are theory which are non-physical, but on the another, so it's a physical thing. What?
It's like an entanglement witness. It's like a theory witness, whether the theory is
Yeah, that's right. But still, I have a problem with this, which I will put to you. I discussed, basically, I need to discuss with you the problem which
you have very little time left.
Okay. So to understand how, let us look at another scenario, which is a Van Damme protocol, some guy from Oxford who has discovered a protocol. So,
okay.
So in this case, Alice receives 2 bits, A0 and A1.
Okay.
Alice can send only 1 bit to Bob. So M equal to 1.
Mm-hmm.
Okay?
Okay.
Alice and Bob share a no signaling box. The correlation between the input AB and the outputs of the box are given by A XOR B equal to AB. So it's like, basically it's a PR box.
Okay.
Yeah. And the no signaling is satisfied due to uniformly random local outputs. So the local outputs are such that Alice and Bob, they can't communicate basically. Fine?
Okay.
Yeah. And Bob is asked to guess A0 and A1.
Okay.
So Alice sends 1 bit and Bob is asked to guess both A0 and A1 in this case.
Okay. Okay.
So B equal to 0 as well as 1 here. So this is the scenario. So you can see that A0 and A1 is given to Alice. Bob is given.
It's the same picture. Bugger.
No, it's not the same picture. So here I have a protocol. It's in the earlier case you didn't have this.
I'm saying that in a different paper he's used the same picture. I mean, same background and added things.
Yeah. Actually, and I think it might be the reason why he put the equal to thing there, but it's not equal to in the earlier picture.
Okay.
So the earlier picture is wrong.
Okay.
Yeah. So this Van Damme's protocol that is used to solve this problem. So what Alice does, that uses A0 plus A1 as an input to the shared no signaling box and obtains the outcome A. So you can see this in this box, she puts A0 plus A1 and she gets the output A.
Mm-hmm.
And then she uses this A to send her message. So she can, if she wants to send A0, then she will XOR A0 bit A and send it to Bob. Or A1, then she will XOR A1 bit A and send it to Bob.
Okay.
Now Bob wants to get the value of A0 or A1.
Okay.
Suppose he wants to get A0, then he will feed B equal to 0 in this box.
Okay.
And he gets the output B.
Okay.
And whatever output he gets B, he XORs it with the message which came from Alice.
Okay.
So the overall, so the AB becomes X plus B equal to A0 plus A plus B.
X plus, say it again.
So AB equal to, now you put simply value of X here in the AB. So AB is X plus B and X is A0 plus A. So AB equal to A0 plus A plus B.
What is AB?
What is AB is here the value of Bth bit of Alice.
Okay, because there is a capital B, there is a A, and then you were saying AB, and there is no AB in the diagram, so I was getting confused.
You can see AB in the diagram, right?
I can't see AB in the diagram. Where is AB in the diagram?
You
Oh,
can
it
see the
looks like
banners.
A0. Ah, okay.
Bottom thing here. Uh,
You don't have a mouse pointer?
I have a mouse pointer. I'm pointing it on AB.
I can't even see a mouse pointer. What the hell?
Fine. Okay. So you can
No,
see
no,
this.
must be the presentation mode, something like that, that it disables the mouse point. Okay, never mind. I understand, I suppose, roughly.
Now
Okay.
you can see it here.
Yeah, see, the thing is that your slide is not full screen anyway. I mean, I can't see the slide in the whole area, and the picture is extremely small. So,
Fine.
are
So
you in full screen?
I'm full screen,
Why is
but
the slide small then? I mean, I can see a big thing and it's still not. Can't you zoom? Damn you, Kishore. Yeah, zoom it in
can,
further. At least I can see the slide. Huh,
can
it's
you
pretty
see
nice.
AB?
Okay.
Okay. So AB is X plus B,
Okay.
and X is A0 plus A.
X is A0 plus A. Okay. So it's A0 plus A plus B. Okay.
So if A plus B equal to 0,
Okay.
then he can happen to know about
A0.
A0.
Yeah.
And if it's 1, then he will know about A1. Right?
Okay.
Okay. So Bob uses A to compute her message. Oh, sorry, Alice uses A to compute her message, which is A0 plus A. Sends it to Bob. Bob inputs 0 if he wants to learn A0 or 1 otherwise. Bob gets B as output from the no signaling box. Then he calculates his message beta, the guess, sorry, not the message, guess, which is X plus beta A0 plus A plus B. So the probability that Bob correctly guess A0 is this thing. The probability that A plus B equal to 0 when both A and B both are 0. You
Okay.
understand? Or when A plus B equal to 0, such that if Alice sent Alice output was 1 and Bob gives 0. So Bob is always giving 0 when he wants to know about A0.
Oh, okay. Kishore, we've actually exceeded the time by 5 minutes already. Uh, Maybe since it's getting a little more careful to analyze, we can maybe continue next time. Is that okay? How much is left?
I think it's almost over. So like just wait for like give me 10 minutes.
10 minutes. That will completely mess up the schedule.
Or maybe I just complete this thing and discuss about
I think it'll be very nice if you can do it a little more slowly next time and complete the calculations also. I think it's really interesting.
yeah but no it's very difficult to me to leave at this point because because we will see something magical coming.
I suggest we do it in the end then. I mean, we can stop the hangout. We can do it in the end once and then we can repeat the calculation properly next time also.
It's almost over. Just like if you don't understand, believe for the moment, and then I will do it after the hangout calculations and all.
Yeah, but we've already exceeded, we've exceeded 7 minutes now, Kishore.
Just 5 minutes. Just 1 minute. Okay. So you calculate the probability of getting A0, and then you calculate the probability of getting A1, and finally you have the CSS like parameter, which is sum of this thing, which is 2 of P1 plus P2. So this thing is basically this thing has been put on operational term and is theory independent. And the classical correlation, they are bounded by this value, S classical equal to 3. Quantum correlation, they go up to 2 plus root 2. We can write the probability as half into 1 plus E, and the E lies between 0 to 1. The Shilson bond in this case is EQ equal to 1 by root 2, which you can compare with with this thing here, S equal to 2 plus root 2. So we get EQ equal to 1 by root 2. And as you see that as E exceeds EQ, I becomes greater than 1. So as we go above the value, the bond put by quantum mechanics, information causality fails.
Okay.
Yeah. So this principle helps us in distinguishing between physically realized correlation from non-physical ones. It also generalizes no signaling, but this principle is not so appealing to me because it doesn't seem to distinguish between degenerate theories. So by degenerate theory, what I mean that, for example, I asked you this question, right? That does Bohmian mechanics gives you this bound of 2 root 2?
Yeah.
And you said yes, right?
Yes, it does.
Yeah. So as it turns out, it just gives me a bound on, it gives me a Chilson bound, this information causality principle, but it doesn't help to distinguish me between quantum theory and basically the old quantum theory and the Bohmian mechanics. So the principle will not lead you to quantum mechanics, right? It can lead you to, because it's not one-to-one mapping or something.
Okay.
And it also tries to derive quantum mechanics within its framework. So you can see that in the definition itself, it says that the bits transferred are not quantum bits and all. It uses the words like quantum, classical and all in its definition itself. So
Okay.
if you want to have like derive quantum theory and all, you should need to come out of the formalism of quantum theory and derive quantum theory.
Okay.
So it's one of the things why I think this principle is not so appealing. And I leave it to the audience to think like what can be possible attempts in this direction. And like for me, it's really a nice question to like think of, because at the moment like people are running to quantize gravity and all, but it might be that there is some loophole at the very basic level, and if you fix that, maybe everything falls in place. So that's it.
Okay. So thank you, Kishore, for for that brilliant talk. It was a lot of fun. And what else? You can put on your camera if you don't mind. Be nice. Okay. So, all right. Now we move on to the next section, which was the revision section. We just have 20 minutes this time. So let's get to it quickly. Let me share my screen. All right. Okay. So, all right. Let's start with recalling what we had done last time. So we were looking at energy. We defined what are called integrals of motion. So these will be the 2s quantities that you get after as constants during the motion by solving the differential equation. And the claim was that the number of independent integrals of motion for a closed system with s degrees of freedom is 2s minus 1. Okay. Now the remark is that some constants of motion that arise from homogeneity and isotropy of space have special importance, and we looked at the homogeneity that is given by time. So if we assume that del L by del t is 0, or that any change under sending t to t plus delta t is 0, would effectively mean that when you write dl by dt, the del L by del t term will not be there. And when you do the calculation, you find that this expression here, which is the term for energy, does not evolve with time. Okay? And this holds only when the Lagrangian is independent of time. So that means the potential that you have, that doesn't depend explicitly on time. Okay? But it must be said that if you have a time independent external field, then also it is fine. I mean, so we derived this for a closed system, but even if it is a system in which the system is not closed, it's exposed to some external fields, and you're not putting that in your system, it will still work, which is to say the energy will still be constant. Okay. Now the Lagrangian of a closed system can be written in this form, t minus u, where t is the quadratic function of the velocities, which we discussed last time. So so it's basically half mv square, and instead of the coordinates x, you're using the generalized coordinates q. Kishore, are you able to hear? Is everything all right?
No, everything is alright.
Okay, cool. So now from Euler's theorem, we know, okay, so I don't know the Euler's theorem exactly, but the idea, well, the claim is that you can write del L by, so you remember the Lagrangian is a function of q and q dot. So when you write del L by del q dot, you're only looking at the velocity part, because the potentials do not depend on the velocity. But that's the kind of system we are considering. So we're not looking at viscosity and things like that.
Yeah, and magnetic.
Yeah. So we're not considering those things. So del L by del Q dot into Q dot will effectively be the same as Q dot into del T by del Q dot. And this will be equal to 2t. Okay. So it's extremely simple to check for a case of half mv square. So if you have half mv square, you take the derivative with respect to v, you get what? Mv's. And you multiply it with v, you get mv square. So that's twice the kinetic energy, half mv square. You can also show this works for generalized coordinates. So instead of having a quadratic form always, you can have a form of this type. Where did it go? just a second. So you can have a form of this type. So you can have qi qk dot. Okay, and this is just a function which depends on the coordinates. So even in this general form, you can show that. I mean, I would show it to you, but I don't have it scanned. So, but it's fairly simple. One can check it. Okay, so this 2t, you don't have to take it on my word. You can verify it yourself. All right. Now we know that if you substitute this in the expression for energy, which was given over here, so this expression, so this del L by del Q dot is the term that we were massaging, and now we finally got it to 2t. So that means your energy can be written as T minus U. Sorry, the Lagrangian can be written as T minus U. You add a 2t to it, and it becomes a T plus U. Okay, so that's what I think roughly where we had ended last time. That the energy is a sum of kinetic energy and potential energies. It's written in the Cartesian coordinates here. Okay.
Mhm.
Brilliant. Now let's go to momentum. So homogeneity of space. All right. So just like we did a homogeneity of time, where we said if we send time to t, we send t to t plus delta t, and in that the Lagrangian should not change, which is the same as saying del L by del t should be 0. Here, what we do is, since it's a vector, we have to be a little more careful. So we write, we say r goes to r plus epsilon, and the change in the Lagrangian should be 0 is what we're demanding, which will just be del L by del Ra into delta Ra, where A is the component, obviously. The sum is over the component. Now, so this will be equal to, since your delta Ra is epsilon into del L by del Ra, and since delta L is 0, it means that del L by del Ra will be, the sum of this should be 0. Yeah. Okay. Now, this also implies that if this object is 0, the time derivative of this object will also be 0. No, sorry, they've used the Euler-Lagrange.
Euler-Lagrange.
Yeah, they've used the Euler-Lagrange equation, and then they've used the fact that, so they've just said that this expression must be 0. They've taken the time derivative out because the summation doesn't depend on time. And, sorry?
Lagrangian doesn't depend on time, so. Since the Lagrangian doesn't depend on time, they can take d by dt.
The Lagrangian, it doesn't explicitly depend on time, but it might dependently, implicitly depend on time, right? So you can't say that d by dt is.
So d by dt.
Then the Euler-Lagrange will disappear. What are you saying, Kishore?
Okay, so it's
just the summation is over the index A, and this d by dt is linear, so you can get the summation inside. That is all.
Okay.
Right. Okay.
Yeah.
So you'll have this expression. Now, what you're saying is that whatever expression is inside is independent of time. So that will be a constant of time. That's precisely what you were trying to show. So then we are able to define a new quantity, which we call momentum. And this is supposed to be considered for a closed system. Okay.
Mm-hmm.
Where did the closeness of the system come? I should stress on that. If you have an external field in the system, then the external field usually depends on the coordinate. Okay.
Mm-hmm.
So in that case, a change in the origin of the system will cause change in the system's description. Whereas if you have only closed particles, then if you shift the origin, nothing will change.
Adu, can you hold on for 2 minutes? Somebody has come. Like,
yeah. Okay.
Just a minute. Maya. Maya.
Okay, so we were saying that if you have, so P is going to be conserved for a closed system. So the important condition is closed system. And remember, for time, we said it was okay to have external fields. In this case, it's not okay to have external fields. Okay, so you have to keep those things in mind. So it's yeah, maybe you can think of a harmonic oscillator with an external potential. So the energy of the harmonic oscillator remains constant, but the momentum does not. Okay.
Yeah. Mm-hmm.
All right. So now, if the Lagrangian, so now you can write the Lagrangian in the standard form, Cartesian form. Then your momentum in that case will become ma/va square. Okay. Mm-hmm. All right. So the momentum of the system is the sum of momentum of its individual parts. So Pa is equal to ma/va.
Mm-hmm.
All right. So that's there. And oh, okay. So that's more of a no. So momentum. Okay, yeah. So the
So,
notation is a little. Okay, sure. Okay, all right. So next is that all three components of P are conserved in the absence of external field, right? That we already saw. But if there is the external field, then if the potential energy in the field doesn't depend on all Cartesian coordinates, all right, then those coordinates corresponding momentum is conserved. Okay, that is obvious. Why?
yeah,
Because
but then del L by del Q for those things are zero
yeah. So whatever coordinate you're using, R or Q or whatever it is, that particular coordinate you can always use
from
for
your, yeah.
deriving a constant.
Yeah.
Second remark is physically, you know that del L by del RA is equal to minus del U by del RA,
Yeah,
right?
from Lagrange. Yeah.
Because the first part is kinetic, so there will be no dependence, and this is equal to minus 12. Okay, so this is equal to the force
Yeah.
on the particle. Okay, so this
Right.
is the Newton's law then, and the conservation actually tells you that the net force in a closed system is zero. Okay,
Yeah.
and
Yeah.
this is where the closed system part again comes in. So if you don't have force in one direction, even then you can say net force along one direction is zero, and then you can still conserve momentum along that. And these things we already know, so there's no problem.
Yeah.
Okay, so generalized momenta is the motion is described by generalized coordinates qi, then pi is equal to del L by qi del qi dot.
Mhm.
Okay, so instead of using Cartesian, you use q, and the generalized forces then become del L by del qi, right?
Mhm.
And the Lagrangian equation become pi dot is equal to fi. So this is very useful when you're looking at circular motion and things like that. So you can just use appropriate r theta coordinates and things like that, and then you can get your forces, generalized forces and things. Get quite
Mhm.
simple. Okay, in Cartesian coordinates, the generalized momenta are components of pa.
Mhm.
Yeah.
Yeah. Uh,
Okay. Cool. Now let's go on to center of mass. The momentum of a closed system has a different value in different inertial frames of reference.
Mhm.
Okay. So
Mhm.
let k prime and k be two inertial frames. K prime moves with velocity v with respect to k. Okay. And
Mhm.
I haven't read this part beforehand to tell you, so I may be slow or make mistakes. We can probably note them down and look at them next time.
So maybe I think maybe we can discuss it next time. Because
Yeah.
so
I think we've just done 10 minutes, so we should at least make some progress. I mean, we've been on chapter 2 for a long time. We should
I see.
at least do half of it. Yeah. Otherwise, we'll not make any progress. It will take years to finish this. Okay. So let k prime and k be two inertial frames. K prime moves with velocity v with respect to k. Okay. Now, for a free particle, then we already know that va will be given by va prime plus v. Okay. This is Galilean relativity. Thus, the relation between momenta may be given as p is equal to summation ma va, and then it will become ma v prime and summation v into summation mm. Okay,
Yeah.
and
Yeah.
then this p will be equal to p prime plus v into summation mm. So there
Oh.
exists a frame in which the total momentum is zero, right?
Yeah. Yeah.
Because the forces will
Yeah. Yeah. Galilean transformation.
yeah, okay. So yeah, so you can basically change this value of v such that your p becomes zero, or the other way. And for this condition, then your v will be equal to p by summation mm. Yeah.
Mhm.
Okay.
Mhm.
So then, so this v you can write as summation ma v upon summation mm.
Okay.
Yeah. So this is they found the velocity with which you have to move to go to a frame which has zero momentum. Okay. So generalizing the concept of rest and velocity to a system.
Okay.
Okay. So now you're
Mhm.
talking about a system being at rest and a system having a velocity. So at rest, if the total momentum of a mechanical system is zero in a given frame of reference, the system is said to be so that is at rest relative to the said frame. Okay. So a system will be at rest. So we are earlier only had particles at rest. The system will be at rest when the momentum is zero relative to the frame. Uh, Remark is that the velocity we calculated above gives velocity of the system as a whole. Okay. All right. So from v we can write r. So he's doing it backwards. Okay. So he's first defining the velocity, what the velocity of the whole system should be thought of as okay, which is to go in a frame in which that is the momentum is zero. Then from that, find the velocity of the system. From that velocity, he is now back constructing the position of the particle or the system. All right, which is given as this. It's very nice, to look at it one more time. I mean, brings a smile to my face. Okay, so that V is equal to R dot. Yeah.
Yeah.
Okay. So center of mass, the point at which R points. So that is the center of mass by definition.
Mhm.
Okay. All right. So the remark is the law of conservation of momentum is equivalent to saying that the center of mass moves with a constant velocity. Yeah.
Yeah. Yeah. Law of
Okay.
conservation of momentum. Okay. Yeah.
Okay. So conservation of momentum says what? That L will always be constant for a complete system which is closed. And if L is a constant, then obviously it means R, which is given by uh, so some mass into this velocity V is going to be equal to P. So which is given here, right? So some mass into velocity is going to be P. If P is a constant, that means V is a constant, which means V moves along a straight path. I'm sorry, the particle moves along a straight path since V is a constant. Makes sense, right?
Yeah.
Okay. All right. So now the internal energy. So internal energy is defined as this energy of a mechanical system in a frame in which it is at rest.
Mhm.
Okay. So that is the internal energy by definition. So remark is that the internal energy includes the kinetic energy of the relative motion of the particles in the system and the potential energy of their interaction.
Oh,
Yeah.
uh, now it makes sense, right?
What
So,
makes
yeah, so I used to think of internal energy as the energy of individual atoms and molecules or something, and the system as a whole may not be moving. So, the center of mass velocity, that is zero, but
yes.
because there is kinetic energy of relative motion of the particles in the system,
Yeah.
and there is interaction, and that leads to this internal energy.
Yes, exactly. That's what we do in StatMech, right? All the time. The entire system is at rest, but it's the velocity of the particles that gives the temperature and everything. So that is the
Mhm.
internal energy.
Yeah, yeah.
Yeah, yeah. It's the same. It's the same. Yes, you're right. Okay. So claim is that the total energy of the system when the system's moving along V as a whole is given as E is equal to half mu V square
Mhm.
plus AI.
Mhm.
Okay. And now we'll prove this. Okay. All right. So consider the same old frames K and K prime. So E is given as half summation MAVA square plus U.
Mhm.
Okay. Now
Mhm.
what we can do is we can write VA as VA prime plus V
Mhm.
whole square. Yeah, that's not a problem. You open it up, you get this expression half mu V square. How did mu suddenly pop in? Ah, summation MAV. I didn't define that. That's strange. I normally define things very carefully. Mu. I didn't define mu. That is strange. Okay, seems to be a mistake in the notes, apparently.
Yeah,
Okay,
there is
where
yeah.
it's
Okay.
here,
Okay.
but
Okay. Yeah, it's later. Okay, anyway.
okay. So half mu v square plus v dot this summation plus half MAVA. Okay. So a square plus b square plus 2ab, which is fine, and u over here. That's good. Now this energy can be written as E prime. So E prime will be this plus this, I suppose. Yeah, so this part. This is E prime. This part becomes P prime. And you can you see my mouse or am I just saying this
Yeah,
that?
yeah, yeah. I can see.
Ah, okay. All right. And then you have this half mu v
Okay.
square. All right. So all these terms combined
Mhm.
give you the expression for energy. So now, excuse me. If K prime is the rest frame, then P prime is zero by definition of rest frame.
Mhm.
So that means that your E prime is equal to EI and half mu v square is so mu is the mass and v square is the velocity of the frame. So when the system moving with the velocity v as a whole, its energy will be given by half mu v square plus ei, which is the internal energy.
Yeah.
All right, now let's move on to angular momentum. This is cool stuff. So now you're looking at isotropy of space. Okay. So you say that.
Atul,
Yeah.
वो बंदा बहुत चिल्ला रहा है बे.
अच्छा चल ठीक है. It's actually 58, so we can stop 59 almost. Just a minute. It's not a problem.
आ रहा हूँ 5 मिनट में.
Yeah. Okay. So let me stop this. All right. So that was it. Thanks, Kishore, for the brilliant presentation. I thank myself for the presentation of the topics, and Kishore really has to go. He's in a rush, so we'll continue next time. Stopping and see you